Now I want to prove a very trivial lemma, but because we can learn from the proof of that, so I should just prove this lemma, although it is very simple. If A is a subset of ZD, if A is a finite set and tau is the infimum of all J where Sj is not in A, then there exists C less than infinity and rho less than 1, which depends on A, such that for any x in A, the probability, if we start from x, and the probability of this event is always less than C rho to the n. Remember that rho is less than 1. So when n goes to infinity, this becomes a very small probability. It goes to 0. So the proof is like this. First, a geometric intuition. We have some point x, and x to the boundary, it takes r plus 1 times. So r is the supremum of x when x is in A. So the longest distance. So for any x in A, there is a path of length r plus 1 starting at x and ending outside of A. And so we can say that the probability of this event is lower bounded by 1 over 2d r plus 1. So it's a lattice. So the probability of going is 1 over 2d, 1 over 2d, 1 over 2d. So this passed, for example, and after some time, 1 over 2d, and all of them are independent, and then so you multiply them by together, and then after some time, you get out of this set A. And that's why the probability is at least this fraction. And now we use a simple Markov property that we use in most of the proofs, that the probability, if we start from x and tau is greater than k times r plus 1, this is the probability of, so we write it as the probability that tau greater than k minus 1 times r plus 1 times the probability that tau greater than k times r plus 1 conditioned on this, conditioned on tau greater than k minus 1 times r plus 1. So it's a simple usage of Markov property. Now we can conclude that the probability that tau is greater than k times r plus 1 is upper bounded by rho to the k times r plus 1. And this rho, you just set it as 1 minus 2d to the minus r plus 1. We just substitute that to the 1 over r plus 1. And then the probability that this event, the probability of this event is upper bounded by probability that tau is greater than k times r plus 1. And this is itself less than rho to the k times r plus 1. And then we can write this as rho to the minus k plus minus r plus 1 rho n. And this is the c, that the constant that we are looking for, and the proof is now complete. So now we are interested to prove a theorem that is similar to many of the proofs that I have given, but just because we are now working on the lattice and we want our talk to be complete, so let's just look at this as just a simple review. So if A is a subset of ZD, is a finite set, and F from boundary of A to the R, so this is A, X could go to X plus E, E is just the unit vector, X plus E, X minus E2, X plus E2. So this is X plus E1, this is X plus E2. So the theorem says that the unique function f from A bar to R satisfying delta f of x, Laplacian is 0 for x in A, and f of x is f of x on the boundary, when x is on the boundary of A. And you know tau is just the infimum of all j that Sj is not in A. So we start, and after time you go out of A. So the time that you go out is just S tau, and you know it's a random variable. So the proof is like this. So we can say it is easy to check that f satisfies the Laplacian. So we can say that delta f of x is equal to, just write the definition of the Laplacian, and E is for all of E that is a unit vector. Expectation when you start from x plus E of f of S tau minus, so we close this, and minus expectation if we start from x of f of S tau. So this term is just the average over the neighbor states, or some people say sites, and this part is just 2d times expectation of f of S tau. So this goes with this, and this goes with this, and so this becomes 0. So to show uniqueness, we assume that f satisfies delta f of x equal to 0 on A, and f of x is f of x on the boundary. And then for any x in A, we can say that, and then we can say that Mn is a bounded martingale. Sn minimum with tau is a bounded martingale. And now, because it's a bounded martingale, we can easily use optional sampling, and therefore f of x is expectation of, when it's starting from x of m0, because of optional sampling, it's just m tau, and you know that this is just the definition, that this is just the f of s tau, and we have proved this. Another a little more general theorem is like the same thing, that A is ZD and F is the same thing. It is defined on a boundary. And we have one more function, which is G, from A to R. And then the unique function F from A bar to R, a more general version is like this. So we say that it satisfies minus G of X. So instead of 0, it satisfies minus G of X. So, and F of X is F of X on the boundary. And the solution, the theorem says the solution is the expectation of, if G is 0, we know that it's just f of S tau, as I proved in the previous theorem. But now we have something more. we have something more. Tau minus 1 and g of Sj. And the proof is just similar to the proof of previous theorem that I proved. So now let's move to a different concept, which is harmonic measure, which is very important. Heating probability of a set is a function heating, So for example, that Lovász used to use H for heating, and David Aldous doesn't use H for his symbols. So any mathematician could use a different symbol for convenience. And here we see that another mathematician is using H as well for heating. So H, A, X, and Y is the probability if you start from X that S tau is just Y. And tau is just infimum of J that Sj is in A. So this is important that HA, 0 and Y is a harmonic function in AC. We should say where a harmonic function is. So it is harmonic in A bar complement. And then we define a probability measure on A by just conditioning that the random walk hits A. So HA bar of X and Y is the probability when starting from X that your random walk suddenly hits Y in a finite time, not infinite time. So in infinite time, this is the probability measure that the random walk hits A. And Y is in A. So the harmonic measure of A is the heating probability from infinity, we can say. So this is the limit of HA bar of X and Y when from one vertex from infinity, for example, X from infinity, so the limit is HA of Y. So this is just the probability of escaping the set A and going to infinity. So what is the probability that we escape this random walk, escapes from set A and goes to infinity? So in terms of metric, we say that the distances gets larger and larger and it goes to infinity. So what is the probability? And the lemma that is interesting, it may be obvious, but for some reasons I want to say, first of all, imagine that we have a set A and we have a set B, and we have X starts from here. So X, in order to reach A, it should cross the boundary of B. So this is very important thing, that if you want to go to A, first we should cross the boundary, and then we go there. If we could start from, a random walk could have many different trajectories. Some of them are like this. They come inside and go out, come inside, and they go infinite times, repeat this, and then they go inside to A. And then they reach Y. So just have this picture in your mind. And then now the lemma says that if A is a subset of B and X is in B complement, then HA of X and Y is equal to, I want to relate it to the green function killed at entering A, or let's say leaving A complement. So this is the green function times h of A union with boundary of B, Z, and Y. For any Z in boundary of B. And we want to prove another things as well, that HA bar of X and Y is just H of X and Y divided by summation over all Z, that GA complement of X and Z, PZ tau A is less than tau boundary of B. We want to prove this. So we consider a random time, just a random time, sigma, which is supremum of all j, which is less than tau A, that Sj is in boundary of B. And this is not a stopping time. However, because sigma is less than T of A, we can write the probability that S tau A is equal to Y. We can just write it. There are several conditions. Summation over, because tau A could be 1, tau A could be 2, and this summation is like this. And Sk is Y. For any k, we reach Y. And so this is the summation over k. Now we write this as j equal to 0, k minus 1, z in the boundary. Now we write it as like this. We say that tau A is k and sk is y, and sigma is j, and sj is z. Or in other words, we can say that Px, Sj is Z, and Si is not in A, and I is between J times K from 1 to infinity. The probability when starting from Z, Sk is equal to Y, and Si is not in A union B, where I is K and 1. And this is just the green function, GA complement of X and Z, H of Z and Y. Another theorem that I want to show you, but I don't prove it, is that you have some A, so you have some set A, and then this grows like an evolving set. So sometimes it's C1, C2 goes Cm, and then C infinity, if we can define. And so every path from A, from let's say X, every path from X to A must go through some of these CMs. And the theorem says that, for example, if A is a subset of Cn, where Cn is just the assume a ball of Z less than n, and we define HA of Y, which is the probability if we start from Y, tau A is greater than tau Cm boundary of Cm. If we define this